So in this class, we will solve a problem on deflection. Main thing is here why I have taken this problem is we are going to find out the position of maximum deflection and its value. The question paper problem: a beam of uniform section, a beam of uniform section. The beam of uniform section is 10 meters long. Is 10 meters long. So figure is not given. We have to draw the figure. It is simply supported at its ends. It is simply supported at its ends. It is a simply supported beam. It carries loads of 100 kN and 80 kN. It carries loads of 100 kN and 80 kN at distances of 2 meter and 6 meter respectively. At distances of 2 meter and 6 meter respectively from the left end. From the left end. The question is, calculate the deflection under each load. Calculate the deflection under each load and also maximum deflection. Maximum deflection. Take E is equal to the smallness of the material of the beam 200 GPa, 200 GPa, and the value of I, moment of inertia of the section of the beam 80 into 10 power 8 millimeter power. So this is the problem given. Figure is not there, so we have to draw the figure. So the solution is like this. Let us draw the figure first. A beam of uniform section is 10 meters long. So span of the beam is 10 meters and it is simply supported at the ends A and B. A is the beam. Total span is 10 meters. And he has given that it carries loads of 100 kN and 80 kN a distance of 2 meter and 6 meter from left end. A is the left end. So at 2 meters it carries 100 kN. At 6 meters it carries 80 kN. That means this distance, this 2 meters, this distance is 4 meters. So 2 plus 4 is 6 totally. So this also becomes 4 meters. So I can take this as C and D. Now the question is, calculate the deflection under each load. That means under 80 kN load, that means deflection at C we have to calculate. So the meaning of that is YC we have to calculate. Deflection at D also we require. And the value of maximum deflection, that is Y max. So we will solve this problem by mechanics method. So first thing is to find the reactions. So reactions has to be found out because we have to write the bending moment expression. So RA and RB, they are the reactions. Two reactions are there. So we have to apply equilibrium equations to find the reactions. So for the equilibrium equation, I am going to use sigma Ma is equal to 0, clockwise moments positive, anti-clockwise negative. And here, take the moments of all these forces. 100 into 2 is clockwise moment about A, positive, 100 into 2. Then 80 into 6, that is also clockwise, plus 80 into 6. RB is giving anti-clockwise moment, and the distance is 10 meters from A. RB into 10 is equal to 0. So therefore, RB is equal to, this is 200 plus 480, so it becomes 680. Divided by 10 means 68. So 68 kN is the reaction at B. Positive we got, that means our assumed direction, upward direction is correct. So 68. RB is 68 kN. Then RA can be pronounced by using the another equilibrium equation, that is sigma Fy is equal to 0, or sum of downward forces is equal to sum of upward forces. RA plus RB should be equal to 100 plus 80. So therefore, RA will be equal to 180 minus RB, that is 68, which is 112. So this is also positive, that means upwards only. So RA is 112. So naturally, reactions at the supports which are nearer to the loads, it is more. So RA is greater than RB here. So 200 plus 480 divided by 10. Okay. Now these are the reactions. Once you find the reactions, now let us adopt the Michaelis method. According to Michaelis method, we have to consider a section at the farthest region from the left support. So in case of single support treatment, as I already told, X is measured from the left hand. So I will consider this is the farthest section, dB, farthest portion. So AC, CD, DB, they are the portions. DB is the farthest portion. I will consider section XX at a distance X from A. So this distance is X. Now let me write the bending moment expression at XX, which is Mx. Mx is equal to, so see to the left side, whether you see left side or right side, bending moment due to upward forces is positive, due to downward forces is negative. So sacking and hogging. So R is upward, so bending moment is positive. 112 into X. So I am calculating bending moment at Xx. 112 into X. This is bending moment is negative, minus 100 into X minus 2. So distance from 100 kN to XX section is X minus 2. Then this is also negative, minus 80 into X minus 6. Distance is X minus 6. So according to the deflection equation, Mx is equal to EI into d square y by dx square. So therefore, EI into d square by d square will be equal to this one. 112x minus 100 into x minus 2 minus 80 into x minus 6. So this is the moment equation, bending moment equation. If you integrate this, you will get the slope equation. I will write here integrate with respect to x. So you will be getting EI into dy by dx. Integration of d square by dx minus dy by dx, which is nothing but theta only. Dy by dx is nothing but theta. So is equal to, if I integrate this, 112 into x square by integration of x is x square by 2 minus, we have to treat this x minus 2 as x only, and we have to integrate in Michaelis method. So 100 into x minus 2 whole square by 2, then minus 80 into x minus 6 whole square by 2. So if you simplify this, you will be getting this is 56 x square minus 50 into x minus 2 whole square minus 40 into x minus 6 whole square. This I will call it as equation 1. This is the moment equation. Slope equation. Now, if you integrate this once again with respect to x, you will get the deflection equation. Integrate with respect to x. So the electricity becomes EI into y, because integration of dy by dx is y is equal to 56 into x cube by 3 minus 50 into x minus 2 whole cube by 3 minus 40 into x minus 6 whole cube by 3 plus, of course, here I have to add the constant of integration c1. So here it becomes c1x plus c2. So this is the deflection equation. So 2 is the deflection equation, 1 is the slope equation. Now we have to evaluate the constants of integration c1, c1 and c2 using the boundary conditions. So the boundary conditions are here, since it is simply supported beam, we know that the deflection at the simple supports is 0. So that means there are two supports here, A and B. At A, x is equal to 0 because x is measured from A. At B, x is equal to 10 meters. The total span is 10 meters. So first boundary condition I am going to apply. At A, x is equal to 0, y is equal to 0 because deflection is 0 at the simple support. That is the condition. So this is deflection condition. Therefore, I have to substitute this in equation 2. Substituting in equation 2, LHS becomes 0 here because y is 0. RHS will be, first term will be 0 because x is 0. Second term, if you put x is equal to 0, it becomes 0 minus 2 is minus 2, negative. That term should be omitted. Third term also should be omitted because 0 minus 6 is minus 6, negative. I have to omit. Fourth term, it becomes C1 into 0. The last one C2. So therefore, from this you can say that C2 is equal to 0. This is the first constant of integration. Second boundary condition I am going to take at B, x is equal to 10 meters, y is equal to 0. So here also deflection is 0. So therefore, if you substitute this once again in equation 2, substituting in 2, let us see what we are going to get here. If you substitute this in 2, so LHS once again is 0 because y is 0. RHS, x is, I have to put 10, so 56 into 10 cubed by 3 minus 50 by 3 into 10 minus 3 is 8 cubed minus 40 by 3 into 10 minus 6 is 4 cubed plus C1 into 10. Of course, C2 is 0 from the first condition. So from this you can get the value of C1. C1 will be, so if I take this to the LHS, all these terms if I take to LHS, the signs will be opposite. So first one becomes negative here. So or I can write 10C1. So 10C1 is equal to, first value is minus 56 into 1000 divided by 3. So first value. Then second value becomes plus 50 into 8 cube 50 into 8 cube divided by 3. That is second value. This also becomes plus 40 into 4 cube is 64 divided by 3. So this is the value minus 9280. So minus 9280 minus 9280. Therefore, C1 is minus 928. Let me check once again because the answer should be perfect. These two become plus, this becomes minus. So 40 into 64 divided by 3, first value. Now second value, 50 into 8 cube divided by 3 minus 56 into 1000 divided by 3. So 9280. So C1 is minus 928. Negative only. So once you get these two values of C1 and C2, now substitute these values in the slope and deflection equations to get the general slope and deflection equations. Then later on, after substituting for x values, you can get the corresponding slopes and deflections at the required points. Yeah, now let me substitute that now. So substituting for C1 and C2 in 1 and 2. So I continue. So substituting Substituting for C1 and C2 in 1 and 2. Substituting for C1 and C2 in 1 and 2. So EI into theta, equation 1 becomes EI into theta is equal to 56x square minus 50 into x minus 2 whole square minus 40 into x minus 6 whole square plus C1 is plus minus 920. This equation I will call as equation 3. Similarly, if you substitute for C1 in equation 2, that is deflection equation, you will get EI into dy by dx. Sorry, EI into y is equal to 56 by 3 x cube minus 50 by 3 x minus 2 whole cube minus 40 by 3 x minus 6 whole cube minus 928 x plus 0. C2 is 0. So this is equation 4. Now these two are the general. This is the slope equation. Equation 3 is general slope equation. Equation 4 is general deflection equation. Now just by putting the values of x wherever you may require and substituting and simplifying, we can get the slope and deflection at the required points. But one thing you should keep it in mind is, if any term becomes negative after substitution for x, that negative term should be omitted. It should be neglected. That means it should be taken as 0. Yes, now he has asked the deflections under the nodes. That means yc and y. Let us find out the first step. So first thing, I will take the deflection at C. That is under kilometer node. He has asked under the node. So that means at point C. So if you want deflection at point C, you have to put x is equal to 2. It is 2 meters. In equation 4, because 4 is the deflection equation. So EI into YC is equal to 56 by 3 into 3 cube, 2 cube minus, of course this becomes 0 because 2 minus 2 is 0, and this term 2 minus 6 is minus 4, that is negative, that should be omitted, minus 928 into 2. So this is the YC is equal to, now we will get YC is equal to, let us simplify this RHS, 56 into 8 by 3. 56 into 8 divided by 3, then minus 928 into 2. So you will be getting minus 1706.7. 1706.7 divided by EI. So that EI we will substitute later. This is the deflection at C. So negative sign indicates that it is downward deflection. Next step, to find the deflection under 80 kilonewton node. Second one, to find deflection under 80 kilonewton node, that is at point B. So we need YD now. Once again, put x is equal to 6 meters. That is 6, because at D x value is 6. Here x value is 2. Here x value is 6. So put x is equal to 6. Once again in equation 4. So here we get EI into YD. So we get YD is equal to 56 by 3 into 6 cube minus 50 by 3 into 6 minus 3 is 4 cube. And of course here if you put x is equal to 6, it becomes 0. So this one becomes 0. Minus 928 into 6. So negative terms should be omitted, that's all, within brackets. So if you simplify this, you will get YD is equal to 56 into 6 cube is 216. So 56 into 216 divided by 3 first term minus 50 into 4364 divided by 3 second term, then minus 928 into 6. So you will be getting minus 2602.7 minus 2602.7 divided by 3. So this is the downward deflection, negative means downward deflection. So these two are this thing. Now let us find out the value of EI. So normally EI should be expressed in kilonewton meter square. So that is very important. In this problem we have given E is equal to 200 dpa. 200 dpa means 200 into 10 power 3 Newton per mm square. This let us convert it to kilonewton per meter square. So already I have explained about this procedure in earlier problems. So Newton to kilonewton is minus 3 into 10 power minus 3 divided by millimeter to meter is 10 power minus 3 square. Now if you simplify this, you will be getting V as this will be in kilonewton per meter square. That's what we need. So 200 into 10 power 3, 10 power minus 3. See, this will get cancelled. So this 10 power minus 6 goes to numerator, becomes plus 6, or in other words 2 into 10 power 8 kilonewton per meter square. This is in terms of kilonewton meter square. I value of course he has given in millimeter power 4, 18 into 10 power 8 millimeter power 4. On similar lines, if you convert millimeter to meter, 18 into 10 power 8 into 10 power minus 3 to the power 4. So this is the conversion. So if you convert this, you will be getting 18 into, this is 8, this is minus 12. So it becomes minus 4 power 4. So if you multiply these two values, 2 into 10 power 8 into 18 into 10 power minus 4. So this value will be in kilonewton meter square. So kilonewton per meter square into meter power 4 is kilonewton meter square. If you simplify this is 36 into 10 power 4 kilonewton meter square. So this value of EI we have to substitute in these two. So if you substitute these two values, you will be getting the deflection in meters. Then later on you can convert it into millimeters. So now let us calculate the deflection in meters by substituting in that. So YC, so I will write here, therefore YC is equal to minus 1707.06.7 divided by 36 into 10 power 4. This will be in meters. Let us see what is the value. It is minus 1706.7 divided by 36. It is 47.41. 47.41 into 10 power minus 4. 47.41 into 10 power minus 4 meter. Negative sign indicates that it is downward deflection. So if I want to convert this into millimeters, you have to multiply by 10 power 3, that is 1000. So if you multiply by 10 power 3, it becomes 10 power minus 100 divided by 10. So minus 4.741 mm. So this is the deflection under the 100 kN load. Similarly, YD is equal to minus 2602.7 divided by same value, that is 36 into 10 power 4 meters. This should be in meters. So on similar lines, if you simplify this, 2602.7 divided by 36, it becomes 72.3, of course, 72.3 negative into 10 power minus 4 meter, or it is minus 7.23 millimeters. Okay, so this is also negative sign indicates downward deflection. So we got the values of deflections at C as minus 4.741. So YC is minus 4.741, whereas YD is, that is under 80 kilonewton, it is minus 7.623 millimeter. Now let us see where the maximum deflection occurs. So where the maximum deflection occurs, let us find out that. The maximum deflection occurs at the point where slope is 0. That is the boundary condition we have to use now. So to find maximum deflection, we have to locate the point first where the maximum deflection lies, and then we have to find its value. The maximum deflection will be more than these two values. So I will write here, to find maximum deflection. This is the important step. To find maximum deflection, Y max. So first we have to find where the maximum deflection occurs. So according to the boundary condition, we can say that maximum deflection occurs at the section where slope or rotation, is theta, is 0. Very important. Now normally we have to assume, in such case we have to assume, so in the case like this, there are two concentrated loads acting. Here the deflection is of course 4.741. Here the deflection is 7.23. Now let us see, we will assume that the maximum deflection occurs somewhere in between C and D. So let maximum deflection, because the effect of both the loads will be there if you consider a section somewhere here. So maximum deflection occur at point E. I will take between C and D. This step is important. We have to assume that it occurs at some point between C and D. Now let us see how the maximum deflection is found out. So C is here, D is here, this is 100 kilonewton, this is 80 kilonewton. Now here, somewhere here I will take maximum deflection to occur. I will take somewhere here, E, we don't know the distance. So if you draw the elastic curve, so it will be something like this. Maximum deflection occurs here, that is in here. If you draw the deflected curve, my max will be here, like this. This is the deflected curve. So this value YE is nothing but your Y max. So we need to find the location of this point E. It is not exactly at the center because the load is not symmetrical. If the load is symmetrical, then we can say that maximum deflection occurs at the midspan point, which I have done in the first problem. So here, first thing, the condition here is if you draw a tangent to this deflected curve. So this is the deflected curve or elastic curve. If you draw a tangent at this point E, the tangent will be parallel to this axis of the beam. That is the meaning of it. Okay. So here theta value, that means theta E will be 0. So the boundary condition now is at E, x is equal to x. X is equal to x or x1. You can take it as x1. Let us find out. Don't confuse with the first x. So x is equal to x1, and you know that theta E is equal to 0. So this is the boundary condition we have to use now. So we know that maximum deflection occurs at the point where slope is 0. So this boundary condition should be used in the equation. What is that? First equation. First equation I have to use. Oh, of course I have put that first equation. What we have to do is here is substituting x is equal to x1 and theta is equal to 0 in equation 2. I think I have to write that equation. I have updated. Let me write that equation. Slope equation I require. So So for getting root equation, of course you need a moment equation. Anyway, I will write both. So what I do here is to get the equation 2, not equation 2, it is equation 1. Moment equation I will write first. EI into d square root by dx square. Already I have written there. Since I have rubbed here, I will write once again. So it is 112x minus 100 into x minus 2, 100 into x minus 2 minus 80 into x minus 6. So this is the moment equation. If you integrate this, you will get the Stokes equation. EA into theta or dy by dx is equal to 56x square minus 100 by 2 is 50 into x minus 2 whole square minus 80 by 2 is 40 into x minus 6 whole square plus C1 is minus 920. This is what? This is the Stokes equation. Now in this I have to substitute this theta is equal to 0. So this is your equation 1. So if you substitute theta as 0, this becomes 0, LHS becomes 0, RHS is x is equal to x1 I have to take. So 56 x1 square minus 50 into x1 minus 2 whole square. Please note that here, if I assume the maximum difflection between C and D, please note that this x1 should be greater than 2, but it should be less than 6. This is the, because at C x is equal to 2, at D x is equal to 6. If you assume that maximum difflection at some point between C and D, that is E, that value of x1 should be in between 2 and 6. That means in between 2 and 6 means this term I have to take, whereas minus this term becomes negative because x1 is, I will write this, then I will cancel, minus 40 into x1 minus 6 whole square minus 928. So here please note that if x1 is less than 6, this term becomes negative. That means you have to neglect this term. So you will be left with now 56 x1 square minus 15 into x1 minus 2 whole square minus 928 is equal to 0. So this is a quadratic equation which we have to solve. Of course, we have to be getting two values of x1, out of which one value is valid. So minus 50 x1 square, I have removed the brackets, a minus b whole square is a square plus b square minus 2ab. So this becomes minus 50 into 4, that is 200, then plus 2 into 4, 200 x1 minus 928 is equal to 0. So if you simplify this, you will be getting 6 x1 square plus 200 x1 minus 1128 is equal to 0, or x1 square, if you divide this 200 by 6, just solving this quadratic equation. So plus 200 by 6, 200 divided by 6 will be 33.33 x1 minus 1128 divided by 6, which is 188 is equal to 0. Therefore x1 will have two values, minus b, that is minus 33.33, plus or minus b square, that is 33.33 whole square, minus 4ac, 4 into a is 1, c is minus 188 under root divided by 2a, 2 into a is 1. Yes, so you will be getting two values. Of course negative value I have to omit. So one value, if you take negative sign here, that we have to omit. So only positive root will take, minus 33.33 plus, take the value of this 33.33 square, minus into minus becomes plus 4 into 188, put it this much, so how much? 1862.9, 1862.9 under root of that. The root of that we have to take, square root of that will be 43.16 divided by 2. So if we simplify this, 43.16 minus 33.33 is equal to divided by 2 4.916 meter. Definitely this value is correct because it lies between 2 and 6. So this is correct answer. The other value will be negative, that we have to omit. So this x1 value now is, that means the distance from the point A to E, this distance is 4.916 meter. So once you get this value, now substitute this value in the deflection equation to get the maximum deflection. Now we know that maximum deflection occurs at point E, which is at a distance of 4.916 meter. Now what we will do here is, we will write the deflection equation and we will substitute the value of x. To write the deflection equation, already it is there. Since I have rubbed here, I will write once again. I have to integrate this one. I have to integrate equation 1 to get deflection equation. I will write here. So the deflection equation, actually this is not 1, this is 3, equation 3. We have to substitute in 3 here. So deflection equation is ei into y. Already it is there, you can just see backwards. So 56 into x cube by 3 minus 50 by 3 into x minus 2 whole cube minus 40 by 3 into x minus 6 whole cube minus 928x. So this is the equation 4 which I have got. In this equation, put x is equal to, we know that maximum deflection occurs when the slope is 0. Slope is 0 and x1 is equal to 4.916. Put x is equal to 4.916 meter in equation 4. So y becomes y max. So ei into y max. So y max and ye. Y max and ye, they are same, is equal to. So put the value of x as 4.916 in that and simplify. The negative term we have to neglect once again here. So this is equal to 56 by 3 into 4.916 cube minus 50 by 3 into 4.916 minus 2 is 2.916. So it is positive, you have to consider that. The third term, you please see here, the third term, if you put x is equal to 4.916 minus 6 becomes negative here. So that term you have to omit. Last term minus 928 into 4.916. So therefore y max is equal to now, so let me write that. Y max is equal to, I have to simplify this now, RHS terms. So I will take 4.916 whole cube, 4.916 whole cube into 56 divided by 3, that is the first term. Second term is minus 2.916 whole cube, 2.916 whole cube into 50 divided by 3. The third term is minus 928 into 4.916. So the value becomes now minus 2757.6. Minus 2757.6 divided by 8. And addition also indicates that it is downward deflection. Now substitute the value of ei as, they have already got the value of ei, 36 into 10 power 4. So minus 2757.6 divided by 36 into 10 power 4. The value are going to be in meter. So we can convert that into millimeter. So this is divided by 36 is equal to. So we have got 76.6 minus 76.6 into 10 power minus 4 meter, or multiply by this 1000 or 10 cube to get in millimeter, minus 7.66 mm. So negative sign indicated is down. That means you can see that the value, the deflection at C was 4.74, at D it was 7.23, whereas at E maximum deflection you are getting 7.6. 66 millimeters. So this is how we had to do deflection problem when they asked you to find out the maximum deflection. So additional condition what we are going to use here, boundary condition, is maximum deflection occurs at the point where the slope is 0. So first we have to locate that slope where the point where the slope is 0, that is the value of x1 we have to find out. Later on, the value of x1 whatever we have got, we have to substitute in the deflection equation and we have to simplify. So this is how we have to do.